Thank you. Good morning. It's lovely to see so many people here. So we learnt before that we have osteoclasts that take bone off, we have osteoblasts that put bone back on, osteocytes that tell them what to do. It's all pretty simple, seems pretty standard, keeps it strong. What if I told you bone could control your diabetes? What if I told you they could do that by monitoring your metabolism, using systems developed in the brain and recapitulated in the bone? So my talk will be a little bit about some of the non-bony things that bone actually does and the potential that we might find from looking at those. So, we've all learnt that bones respond to load. So we look at these two mice, we all know one has a bone that big and one has a bone that big. And now we all know which one's which, right? Except that's not the case, because this guy is a very particular mouse, as you can probably tell already. But he is a very particular mouse, and we learned a great deal about how the bone fits in, the skeleton fits into a far broader system of coordinating our body's activities than we'd previously thought. So this guy, the OB mouse, and no guess what the OB stands for, he does not make just one little protein called leptin, but a very important protein. Leptin is made in your fat cells, and it circulates in your blood, goes to your brain, and it's how your brain monitors how much energy reserves you have. Okay, so he doesn't make leptin, so his brain is absolutely convinced that he is starving. And so what does he do? He eats. And he really eats. Because he's about to die. His brain is convinced that he is on the edge of death. So he eats and he eats and he eats. And it doesn't matter how much he eats, because the part of the brain that monitors how much fat he's got has always come up with a zero. 0, 0, 0, 0. So eat, 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 eat. Okay? So he has constant appetite. And he's big. That's not a stretched image. That is what they're like. And they're lovely, delightful little things. But as we saw from the first slide, what was so surprising, at least to us, about this mouse was that he has less bone. Okay, and he has less bone because he is starving. And so that sets up a competition between weight, and he weighs twice what a normal mouse would, and what the central controlling systems in your brain think, and that is that you are skinny, and so skinny you're about to starve. So why would you waste any energy making bone when you don't need it? And so it sets up a question of who's boss. And in this scenario, it certainly appears that the brain is boss. These monstrous survival pathways will say, no, I don't care what your bones think, we're about to die, and so we're going to suppress everything. And we're going to have a look at how we worked out the process involved in that and some of the fascinating things that have come from it. Now, why does he react like this? Because he has an increase in a protein in the brain called neuropeptide Y. So if you're skinny, your leptin signaling is down, neuropeptide Y comes up and you get hungry and you eat, and you eat, and you eat. And that is to protect you, as it should. Starvation is one of the major ways people will die. So this told us two things. One, the brain controls bone metabolism, we did not know. And two, that this MPY protein is very important to how bone is regulated. And so we thought we would recapitulate that. This is just a tiny part of the brain. If this whole auditorium is the brain, we are looking at my two fists. Probably 1,000 cells in 75 million. So a tiny number of cells. And we just increased how much MPY they made to make this brain starving. And again, here's the body weight. This is 3 weeks. And this is a percentage increase. 50, 60, 70% of their entire body weight they added again with fat. And they would eat and they would eat. They would lie on their backs underneath the food tray and just eat all day. They wouldn't clean themselves. They were like scruffy little teenagers. But what we found is that instead of responding to the weight, they respond to the brain. This is a cross-section of a femur we saw in some of the CTs before. Here's all the cells of the marrow. And all you need to know is that that distance is 1 week of bone formation in a normal animal. And that is what it looks like in the animals that think they're starving. Right? That is the magnitude of the dominance of starvation in evolution. One of the big ways you die, and so we're skinny, don't need bone anyway, let's conserve everything we've got. Okay, and we never knew this was brand new. So, how did it get there? This is a blood vessel, this is again in the marrow, there's a blood vessel. The red is nerves, and they spiral around the blood vessel. The bright green things are the mesenchymal stem cells. They're the baby cells that will grow into bone cells. And you can see how closely these green cells are aligned with the nerves. Let's go even closer. This is a cross-section of an osteoblast, the cells that actually control the formation of bone. And this is a nerve cell, and look, you can see in the close-up, direct signaling. So you have direct channels all the way from your brain, all the way to all the cells of your bone. And so if your brain says something, down the wire it goes, like an old telephone, they had wires, tells them what to do. And so what did we learn about this? So we learnt that, and this is work done here, we learnt that those circuits in the brain, the MPY circuits, are completely recapitulated in the bone cells. So that little system in the brain is exactly the same as in those osteoblasts, the bone-forming cells down in the bone. And so we can modulate it. And this is what we did. So we blocked this signaling, and just in the osteoblast, nowhere else. The rest of the entire body is normal. And so we created a system where they think they're obese. And sure enough, more bone. The MPY goes down, he thinks he's obese, and he grows more bone. Because not only the brain is monitoring your metabolism and responding, like when the brain thought it was starving, it made less bone, the bone cells do it too. So there's a redundancy. So in case the brain has trouble, the bone can pick up the slack. And so in this case, the bone thinks they're big and puts on more bone. But then things got even more interesting. So other things occurred. They got diabetic. Again, this is just a change in bone cells. Not anywhere else, not in your pancreas, not in your brain, just your bone cells. And you can see, hands up who's had a glucose tolerance test. Has anyone been tested? Right, so a few of you know, essentially you put in a bolus of glucose and then you track how insulin does its job to put it back into your cells. And so these mice that think they're obese, they can't make as much insulin. And when we used another model that made more MPY, they made more insulin. And so your bone cells are able to control insulin and glucose, just like diabetes, which we'd never even contemplated before. And through a few years' work, we actually found what it was. We found a protein. So if the bone is changing what goes on in the pancreas, then there has to be a signal. And can we find that signal? And we could. And it is called osteoglycin. And so it is potentially a bone-derived treatment for diabetes, because that's what this protein's job is. Its job is to control your insulin activity and your blood glucose. And here's two aspects of a glucose tolerance test again. And so we put in, it's like having a meal here, a big bolus of glucose, and the blood glucose goes up, and then insulin comes up and puts that glucose back into your cells, and that's what a glucose tolerance is. So the blue line is the normal mouse. We added osteoglycin to this mouse in a little injection, and you can see his glucose doesn't go up as much, and he more rapidly puts that glucose where it needs to go. There's no point it being in your blood, it's dangerous there anyway. Get it into your cells. And this is insulin. So with the addition of with osteoglycin, this animal barely needed any insulin at all to put that glucose away. And so we know the problem with diabetes is you haven't got enough glucose, haven't got enough insulin. So that is a potential cure for a completely different disease coming from bone. So, final slide. So what did we learn? Bone mass is integrated with our metabolic system. It's not just weight, it's how much food you've got and how well you're doing. This happens through nerve circuits in your bone and in your brain. And bone controls your blood glucose through activating and controlling insulin. So what we learn is bone might tell us about completely different diseases that we never thought. Thank you.